Welcome back to our series on alkyne reactions. In this video, we shift our focus from addition reactions to acid-base chemistry and the versatile acetylide anion. Acetylides are strong carbon nucleophiles, formed by removing the acidic proton from a terminal alkyne. They are crucial for synthesizing larger, complex carbon skeletons through new carbon-carbon bond formation. Our focus will be on two key areas: how to generate this acetylide anion from a terminal alkyne, how the acetylide anion participates in substitution reactions to build longer molecular chains. Formation of acetylide anions, the acidity of terminal alkynes. Let's begin by understanding why we can deprotonate an alkyne at all. Terminal alkynes, which have a hydrogen atom attached directly to an 𝑠𝑝-hybridized carbon, are significantly more acidic than alkenes or alkanes. The sp orbital has a higher percentage of S character compared to sp3 and sp2 orbitals, meaning the electrons in the CH bond are held more closely to the nucleus. This increased S character enhances the acidity of the terminal alkyne and helps stabilize the resulting acetylide anion after deprotonation. To compare these acidities, consider the following approximate pKa values. You can see that the alkyne has the lowest pKa value, indicating it is more acidic than alkenes or alkanes. However, even terminal alkynes are still weak acids compared to water or alcohols. To remove this proton efficiently, we must use a very strong base whose conjugate acid has a much higher pKa value. Generation of the acetylide anion. The most common and effective reagent for generating acetylide anions is sodium amide, dissolved in liquid ammonia. Using propyne as our starting material, the reaction proceeds as follows. NaNH2 acts as a strong base, abstracting the acidic proton from the alkyne and generating the acetylide salt. The conjugate acid of the NH2- is NH3, whose pKa is approximately 35 to 38. Because this value is much higher than that of terminal alkynes, NaNH2 acts as a significantly stronger base, and the equilibrium strongly favors formation of the acetylide anion. Once formed, the acetylide anion acts as a strong carbon nucleophile. It can react with alkyl halides to form new carbon-carbon bonds, enabling synthesis of larger alkynes. Reaction with primary alkyl halides. The acetylide anion reacts readily with primary alkyl halides or methyl halides, where the halogen atom is attached to a carbon with minimal steric crowding. As an example, the acetylide of propyne can react with 1-bromobutane. In this process, the acetylide attacks the carbon attached to the halogen, and the halide leaves. This type of transformation is a common way to extend carbon chains in organic synthesis. This reaction is favored because the acetylide ion is a strong nucleophile. Primary alkyl halides are easy to approach. The overall result is the formation of a longer internal alkyne. You can minimize errors by numbering the carbons, such as 1, 2, 3, 4, 5, 6, and 7, to track the chain elongation. We will cover the detailed mechanism of this reaction in a future video on SN2 reactions. Reaction with tertiary alkyl halides. The acetylide anion is also a strong base. When it reacts with highly crowded alkyl halides, a different type of process becomes dominant. For example, when the acetylide of propyne reacts with a tertiary alkyl halide, such as 2-bromo-2-methylbutane, the crowded structure prevents effective carbon-carbon bond formation. Instead, the acetylide removes a nearby hydrogen atom, leading instead to an elimination reaction that produces a Zaitsev-favored alkene, rather than the desired chain-extended alkyne. We will cover the detailed mechanism of this reaction in a future video on E2 reactions. Let's summarize. Terminal alkynes can be converted into acetylide anions using very strong bases such as sodium amide. Acetylide anions act as carbon nucleophiles and are useful for forming new carbon-carbon bonds. Secondary and tertiary alkyl halides tend to undergo competing pathways, typically elimination or rearrangement, instead of the desired substitution with the acetylide anion. Those who wish to deepen their understanding of acetylide reactions are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.